Welcome to the deep dive. Today we're getting into thermodynamics, which, is really the science of energy and how it moves around, how heat flows, how energy changes when, when things happen, physical changes, chemical reactions.
Exactly. And what's really interesting for this deep dive is our source material. It looks like someone's handwritten notes, so like actual student notes trying to get a grip on these core ideas, definitions, properties, the big laws, different processes. You can almost feel the learning process happening on the page.
Right.
So our goal here is to kind of unpack that understanding, pull out the key bits from these notes, make it clear, engaging, and maybe help you have some of those same aha moments.
Okay, sounds good. So where do these notes start? Looks like the very basics, system, surroundings.
Yeah, foundational stuff. The notes define this system as, whatever specific part of the universe we're interested in. It could be tiny, like a reaction in a tube, or bigger, like an engine.
Or just a cup of tea cooling down.
Perfect example.
Yeah.
And then the surroundings are literally everything else outside that system.
Everything.
Everything. And the notes make this point. System plus surroundings equals the universe. Simple, but fundamental. And crucially, there's the boundary separating them.
The line between the system and the unlimited surroundings, as the notes say, puts things in perspective.
It does. And based on what crosses that boundary, the notes categorize systems.
Right, the different types, open, closed.
Exactly. Open systems can exchange both matter and energy. Like that cup of tea, without a lid, steam gets out, heat gets out.
Makes sense.
Then closed systems put a lid on that tea. Matter can't get in or out, but energy, like heat, still can.
Okay. And the third one, isolated. That sounds trickier.
It is, in practice.
Yeah.
An isolated system ideally exchanges nothing, no matter, no energy. The classic example is a perfect thermos flask.
But perfection is hard to come by.
Precisely. The notes are smart to point out that a truly perfect isolated system is more theoretical. Real thermoses aren't quite 100%. But it's a useful concept for thinking things through.
Got it. Open, closed, isolated, based on exchange. Now, to describe these systems, properties, extensive and intensive.
Yeah, another key distinction. Extensive properties depend on how much stuff you have. Mass, volume, total energy. If you double the amount, these double too.
Like 2 cups of tea have double the mass of 1. Simple enough.
Right. Then intensive properties, these don't depend on the amount, just the nature of the substance. Temperature, density, pressure.
So a single drop of water has the same density as the whole ocean.
Exactly. Intensive is about the what, extensive is about the how much.
Okay. And these properties define the state of the system.
That's right. The state is just its condition described by measurable properties like pressure, temperature, volume, and so on. And this leads to a really important idea. State variables, or state functions.
State functions, remind me.
These are properties where only the beginning and end points matter, not how you got there. Think about climbing a mountain. Your change in altitude depends only on the start and finish points, not whether you took the steep path or the winding one.
Right, the path doesn't change the overall height difference.
Exactly. Internal energy, enthalpy, and we'll get to those. They're all state functions. The history doesn't matter, just the initial and final states.
Okay. The notes then talk about processes reversible and irreversible. This sounds fundamental.
It really is. A reversible process is kind of an ideal. It happens incredibly slowly, like infinitesimally slowly. So the system and surroundings are always perfectly in balance, always in equilibrium.
So you could just reverse it perfectly.
In theory, yes. A tiny change could send it back the other way, restoring the initial state completely. And importantly, these theoretical reversible processes get the maximum possible work out of the system.
Sounds unrealistic.
It pretty much is.
Yeah.
Most real-world things, almost everything, happens irreversibly. Think of that coffee cooling down that's spontaneous, driven by a temperature difference. There's no equilibrium within the system itself during the change.
And you can't just make the heat flow back into the coffee from the cool room.
Not without doing some work, putting energy in, changing something else. You can't simply reverse it. And for the same start and end points, an irreversible process always gives you less useful work done by the system than the reversible ideal.
Okay, irreversible is the norm. Now, internal energy. U or E in the notes.
Right. Internal energy, often U or E, is basically the sum total of all the energy within the system. Kinetic energy of molecules moving, potential energy in chemical bonds, all of it.
And it's a state function.
Yes, and its extensive depends on amount. But here's the catch the notes highlight. You can't know its absolute value. What we can measure is the change in internal energy, delta U or delta E.
How does that change?
Through 2 main ways energy crosses the boundary. Heat, Q, and work, W. The notes give that fundamental equation, BE equals Q plus W. The change in internal energy equals the heat added plus the work done on the system.
Heat and work, let's break those down. Heat, Q.
Heat, Q, is energy transferred because there's a temperature difference. Heat flows from hot to cold. The sign convention is key. If heat flows into the system, Q is positive. If heat flows out, Q is negative.
System gains energy, Q is plus. System loses energy, Q is minus.
Got it.
And work, W.
Work, W, is any energy transfer that isn't due to a temperature difference. Could be mechanical work, like a gas expanding and pushing a piston, or electrical work.
Okay, in the sign convention.
If work is done on the system, energy is added, so W is positive. If work is done by the system, it uses energy, so W is negative.
Makes sense. System gains energy, positive W. System does work, negative W. And the notes mention PV work specifically.
Yeah, pressure volume work is super common, especially in chemistry, like gases expanding or being compressed. The equation for that is W equals to BOV, where P is the external pressure and dV is the change in volume.
Okay, so DE equals Q plus W sums up how internal energy changes. This feels like it's leading somewhere big.
It absolutely is. This leads straight into the first law of thermodynamics.
It's a big one.
Well, the first big one, it's really just the law of conservation of energy applied to these systems. It states that energy can't be created or destroyed, only converted from one form to another. The total energy of the universe is constant.
The ultimate energy accounting rule.
You could say that. The co-E Q plus W is the mathematical statement of it. Energy change in the system equals energy flow across the boundary.
And what about for those ideal isolated systems?
Right. For an isolated system, remember, no exchange. So Q equals 0 and W 0. Plug that into the first law.
QA plus 0. So EE equals 0.
Yeah.
The internal energy stays constant.
Exactly. Total energy inside is conserved because nothing gets in or out.
Okay, first law, energy is conserved. Now, the notes go through specific types of processes based on what stays constant.
Yeah, these are helpful categories for analysis. Isothermal means constant temperature, ET equals 0.
Like something happening in a temperature-controlled water bath.
Good example. That isobaric means constant pressure, EP equals 0. Like many reactions in an open beaker, open to the atmosphere.
Okay, isochoric.
Isochoric means constant volume, B equals 0. If volume doesn't change, then that PD work term is 0, right? So W equals 0.
Ah, so for isochoric processes, all EQs plus 0, just EE will kill Q. The energy change is just the heat flow.
Precisely. Then there's adiabatic.
That's the one with no heat exchange.
Correct. Adiabatic means Q equals 0, so any change in internal energy is only due to work done. EE W will do. Think of compressing a gas really fast in an insulated cylinder, no time for heat to escape.
Quick compression or expansion, got it. And finally, cyclic processes.
Cyclic means the system goes through a series of changes but ends up back exactly where it started, like one cycle of an engine. Since state functions only depend on start and end points, and here they're the same.
The net change in state functions must be 0, so GH equals 0 for a full cycle.
Exactly. And AAGH all 0 too, as we'll see. Enthalpy is also a state function.
Okay, these process types are useful scenarios, but the notes also mention limitations of the first law.
Yes, this is crucial. The first law is great for tracking energy. It tells us it's conserved, but it says nothing about direction. It doesn't tell us if a process will happen spontaneously or why heat flows from hot to cold and not the other way.
Like a broken cup doesn't spontaneously reassemble, even though energy would be conserved if it did.
Perfect example. The first law allows it, but it doesn't happen. We need something more to predict spontaneity.
Which brings us to enthalpy, H.
Enthalpy, H, defined as HE plus PV. It combines internal energy with this pressure volume term. Now, why is this useful? Because, as the notes highlight, so many processes happen at constant pressure.
Like reactions in open lab beakers again.
Exactly. Exposed to constant atmospheric pressure. And under those specific constant pressure conditions, the heat exchange, which we often call Q at constant pressure, turns out to be exactly equal to the change in enthalpy, H.
Ah, so AH euro. That makes enthalpy really handy for measuring heat in common lab setup.
Extremely handy. It lets us track heat flow easily in many real-world chemical and physical changes. And like E, enthalpy H is also a state function and an extensive property.
So again, we usually talk about the change, AH.
Right. HEH, each final H initial, or you can relate it back to internal energy. ATA plus PE for constant pressure processes.
Okay. The notes then apply this to chemical reactions, the heat of reaction.
Yeah, the enthalpy change for a reaction, AG, is just H products, H reactants. This tells us if the reaction releases heat or absorbs it.
Exothermic versus endothermic.
Exactly. If H is negative, Products have lower enthalpy, energy is released that's exothermic, feels hot. If each is positive, products have higher enthalpy, energy is absorbed that's endothermic, feels cold.
Simple sign convention.
Yeah.
And this applies to physical changes too. Melting, boiling.
Absolutely. Enthalpy of fusion, melting, enthalpy of vaporization, boiling, sublimation, solid to gas, even dissolving something, enthalpy of solution. They all involve energy changes, breaking or forming intermolecular forces, which we track as...
Makes sense. The notes also specify heat of combustion.
Right, that's the HH, when 1 mole of something burns completely in oxygen. It's always exothermic. H is negative. That's related to the fuel value or caloric value of substances.
How much energy you get out. What about enthalpy of formation? Sounds like a reference point.
It is. The standard enthalpy of formation, HE0 AC E20 by 820 by 98, is the enthalpy change when you form 1 mole of a compound directly from its constituent elements with everything in its standard state, usually 25 degrees C, 1 atmosphere pressure.
Why is that useful?
Because these values are tabulated for tons of compounds. And using them, along with some rules, lets you calculate HH for almost any reaction.
What rules? The notes mention laws of thermochemistry.
Yeah. First is the Lavoisier-Laplace law. Super simple. If you reverse a reaction, the sign HE flips, but the magnitude stays the same. H reverse.
Makes sense. Forming a bond releases energy. Breaking it costs the same amount.
Exactly. And the other big one is Hess's law of constant heat summation.
That sounds important.
It's incredibly useful. Hess's law says the total enthalpy change for a reaction depends only on the start and end points, not the intermediate steps or pathway.
Like state functions again?
Precisely. So if you can express a target reaction as a sum of other reactions whose H values you do know, like those formation reactions, you can just add up those known H values algebraically to find the H for your target reaction, even if you can't measure it directly.
A very clever calculation trick.
It's more than a trick. It's a fundamental consequence of enthalpy being a state function. The notes also mention bond dissociation energy here.
How does that fit in?
Bond energy is the energy needed to break 1 mole of a specific type of bond in the gas phase. You can estimate the HH for a reaction by summing up the energy needed to break all the reactant bonds and subtracting the energy released when all the product bonds form.
So H is roughly energy to break bonds minus energy released forming bonds.
Yep. Bond energies of reactants, bond energies of products. It's an approximation, but often a pretty good one.
Okay. Breaking requires input, forming releases output. Got it. Now, back to that limitation of the first law. Spontaneity.
Right. Spontaneous processes are those that happen on their own, without needing continuous external help. Rust forming, ice melting above freezing, gas expanding into a vacuum.
Things that just happen.
Pretty much. And the notes point to 2 tendencies driving spontaneity. A move towards lower energy, like that negative H for exothermic reactions, and a move towards greater randomness or disorder.
Lower energy makes sense, but more disorder, that sounds like.
Entropy. That's exactly where we're headed. Entropy, symbol S, is the measure of randomness or disorder in a system.
Okay, measuring chaos.
In a way, yes. It's also a state function, and it's expensive. Higher entropy means more disorder, more ways for the system's components, atoms, molecules, to be arranged.
And this helps explain spontaneity.
It's the key to the second law of thermodynamics, which does address direction and spontaneity. Mathematically, for a reversible process, the entropy change, AASS, is the heat exchanged reversibly, CREV, divided by the absolute temperature, T-blit, AS.
Units are energy per temperature, like joules per Kelvin.
Correct, JK. And for a reaction, S products, reactants.
What's the physical intuition? Why does disorder matter?
Think about states. Gases have way more entropy than liquids, which have more than solids. Why? Gas particles are zipping around randomly, occupying a large volume, tons of possible arrangements. Solids. Particles are locked in place, very ordered, few arrangements.
So more freedom of movement, more possible arrangements means higher entropy. Like a messy room has higher entropy than a tidy one.
That's a classic analogy. Many ways for things to be messy, fewer ways for things to be perfectly ordered. Nature tends towards the states with more possibilities, the more probable, more disordered states.
Okay, systems tend towards higher entropy. But what about the surroundings? Didn't the first law involve both?
Excellent point.
Oh.
The second law, in its most powerful form, talks about the universe. It states that for any spontaneous process, the total entropy of the universe, system plus surroundings, must increase.
So each universe S system plus surroundings. And this must be greater than 0 for something to happen on its own.
Exactly. So universe 0 for spontaneous. Universe 0 means the reverse process is spontaneous. And if universe equals 0, the system is at equilibrium, no tendency to change.
Okay. But tracking the entropy of the entire universe seems difficult.
It can be. That's why scientists came up with another concept that focuses just on the system, but implicitly includes the surroundings effect, especially under common conditions. And that's Gibbs free energy.
Ah, G. The notes define it as GHTS.
Right. Gibbs free energy, G, combines enthalpy, H, and entropy, S, with temperature, T. It's another state function, also extensive. And the change in Gibbs free energy, G, at constant temperature and pressure is the ultimate indicator of spontaneity.
So this is the number we look at?
This is usually the most convenient one, yes. The change is given by GHTS.
Okay, GHTS. How does its sign tell us about spontaneity?
It's simple. If day G0 negative, the process is spontaneous under those conditions, constant T and P. If day G0 positive, it's non-spontaneous. If dg equals 0, the system is at equilibrium.
Negative G means go. Positive G means no go. 0G means equilibrium.
You've got it. And there's more. Day G also represents the maximum amount of useful work, non-PV work, like electrical work, that can be extracted from a process at constant T and P.
Right.
dg equals useful.
So a negative G means the system can do useful work.
Yes. And it also connects directly to the equilibrium constant, cake for it, a reaction through Ag0 as stores RTLN cake, where R is the gas constant. This links the thermodynamic tendency to the actual position of equilibrium. Yeah.
Okay, so day G ties together enthalpy, entropy, temperature, spontaneity, useful work, and equilibrium. That's quite central.
It really is a cornerstone of chemical thermodynamics. It brings everything together to give us a practical way to predict if reactions will proceed.
Now, the notes end by looking at how temperature affects this G equals HET equation.
Right, because temperature multiplies the entropy term. Or in T, it can change the balance, and thus the sign of D.
How does that work? Depends on the signs of H and D.
Exactly. Let's consider the cases. Case 1. If AH is negative, exothermic, and AD is positive, more disorder, then D will always be negative, regardless of your endothermic and alloy temperatures.
Favorable enthalpy, favorable entropy. Makes sense.
Case 2. If AD is positive, endothermic, and DE is negative, less disorder, then GAD will always be positive, non-spontaneous at all temperatures.
Unfavorable enthalpy, unfavorable entropy. Also makes sense.
Case 3. If both H and D are positive, endothermic, more disorder. Here, the day G employs plus T plus. At low T, AH dominates, G is positive, non-spontaneous. But at high T, the negative T term becomes large and negative, potentially making DD as spontaneous.
Like melting ice, needs heat, becomes more disordered. Only happens above a certain temperature, 0 degrees.
Perfect example. And case 4. If both H and A are negative, exothermic less disorder, DGAG. At low T, the negative H dominates, DG is negative, spontaneous. At high T, the negative T term becomes large and positive, potentially making D positive non-spontaneous.
So knowing H and S lets you predict the temperature range where a process might become spontaneous or stop being spontaneous. That's incredibly powerful.
It really is. Understanding these relationships, first law for energy accounting, second law on entropy for direction, enthalpy for heat at constant pressure, and Gibbs energy to tie it all together for spontaneity, gives you a framework to analyze almost any energy change or process.
Absolutely. Looking back at these notes, you can really see the student building that framework piece by piece. Those connections between the laws, enthalpy, entropy, Gibbs energy, they really clarify why things happen the way they do.
It's quite profound when it clicks. And it leaves you thinking, doesn't it? This universal tendency towards increasing entropy, universe always going up for anything that happens.
The universe getting messier.
On a fundamental level, yes. What does that mean for everything? For the structure we see around us, for the direction of time itself? If the ultimate fate is maximum disorder, what are the implications of that relentless thermodynamic drive?
A big question indeed, something for all of us to ponder. Thanks for unpacking those thermodynamics notes with us today.